Good afternoon. It's Wednesday, the end of April, 2023. Now, a lot of these talks these days have been about the path integral. And the path integral is a particular form of line integral that in the world of wave equations, the Schrödinger picture, as the Heisenberg picture goes to it, that the path integral is basically is a discovery or an invention or derivation of Richard Feynman. And Feynman is a pretty famous, as far as physicists go, the public knows who he is. He's a famous physicist. Compared to that, otherwise, the most famous physicist that anybody ever knows is Einstein, Albert Einstein. I don't really recall if Einstein has a middle name or what. It's just Einstein, or Albert Einstein. So anyways, one thing one might wonder is, well, Einstein has this annus mirabilis, his miracle year, 1905 or so, and he was working at the office of the intellectual property or patent laws in Switzerland or somewheres, and thus he had access to all sorts of inventions, ideas, and da-da-da-da-da. And from what I understand, he was married as a young man in his early 20s or so, and that his wife was also very involved in the mathematics. In fact, it was highly exceptional at that time for a woman to have a college education, and she had graduated with some honors from a summer program in physics. So though he worked at a patent office and his trade and profession was basically marking papers and doing patent research, then it is well that he was able to absorb a lot of the philosophical grounds, the technical grounds, the grounds of the research and the tools of the day, linear algebra, quite a ways after Poincare, the geometric and coordinate approach and the covariant approach to linear algebra, and then with regards to usual notions of kinematics and kinetics, or physics, as most people think of it, as in terms of statics and dynamics, the matters of massy bodies, the Newtonian. Then also he was familiar with electricity, magnetism, and ... and the various experiments at the time that were in quite a very successfully fruitful time for the study of the subatomic nature of particles and the atomic nature of particles. That elementary chemistry had been coming a long ways, and there was since discovery of oxygen as a separate substance and its role in combustion, or the discovery of the electron, the proton, the neutron, and these various stoichiometric ratios of atoms, and the development of the atomic models of the nucleus of the atom, and such matters. That it's called annus mirabilis, whereas for such a young man in such a wide field, that his authored papers on the optoelectronic effect as for about electrons and special relativity, and then later for general relativity, made a huge splash, huge impact. He later went on. I don't know too much about his life really, but I can kind of just picture him, pulling his pouch out of his pocket and pulling his pipe out of his pouch and putting in his pipe who knows what, and puffing on it and detailing both kind of lyrically or in the sense of a story and reflections on these things, and as well then in the mathematics that according to the mathematics of the existence of a metric and basically putting the space and time together, and that he was able to write up for some basically equations for Lorentz. After the Galilean invariance, there's a Lorentz invariance where it can be kind of considered in terms of space and time, and what with regards to then there's in some models, there's only a ray of time, for example. Then in others, there's a two-sided ray or a vector, or a two-sided vector of a dimension of time. Vis-a-vis that in the Euclidean, then there's any matters of Cartesian orthonormal vector basis spaces, like the most familiar R and R squared and R cubed, space-time. Whereas this is largely after Minkowski, that the Minkowskian is the basic establishment of these 3+1 dimensions as a background or as space that contains within it all such bodies of matter universally. This is basically assumed that whether there's a universe infinite or not, that there's a universe, and thus that from any given origin, and the idea of relativity is that there's no privileged frame, there's no absolute origin, and that every single thing has its own frame, and those are all nested together as frames. And so as an original analysis, it's really just not so different from the Euclidean space and assigning it an origin and calling it Cartesian space, just saying that it's a Euclidean space. That then some various methods in the tensorial products and a various convention that makes things easy to write the formulas. That it results that Einstein's derivations are pretty easy to write out, once it only takes so much to do to write out what all that they imply for relativity and the theories of relativity. Here's special relativity, which governs light, and general relativity, which governs matter. And then as with regards to whether charge is regulated by special relativity or general relativity, that it kind of depends on the medium, that otherwise it's a charge in space, which is as well that the motion of electrons is bradyonic, meaning slower than light, and that as far as that goes, light in deep space as a vacuum is considered tachyonic to the speed of light to light through any other medium. That light speed in this model is a constant, which is then so very critical in all matters of range finding and things that reflect the distance between an image and its source and these sorts of things. This, while it's still so that it's well known that in the solar system, that even though the image we see at any given moment of another planet like Mars or Jupiter is as far behind where it really is the source in the ephemeris, any geodesy in their orbits, that gravity always points at the source and changes are instantaneous. That if a million green men on the moon suddenly jumped up and down and bounced it any way out of orbit, it would instantaneously affect Earth's orbit around the sun. And so this is that things as they orbit together, they're basically falling together in terms of orbital trajectories, and that two passing bodies of any sort are orbiting each other. And then there's then decaying orbits which lead to collisions, or non-decaying orbits which lead to passage or relative transits of motion. So anyways, the other day I was wondering myself, and as I began that long-winded utterance, it's along the lines like, well, I wonder what Einstein was thinking. I wonder what's on his mind. I'd like to know more about him. I'd like to know more about his thinking about things. But luckily, he left a lot of great quotes, and in his years as he grew on and achieved world fame and became a lion of the establishment and was invited to be the first president of Israel and was a well-known Zionist and was a well-known anti-nuclear war type and a sort of pacifist, and that he was well regarded for his violin playing, and he always was puffing on his pipe. That as we relate that to then the sign of the times and how all then that's enshrined, and that there's some very particulars of Einstein that are so great that when I think about it as mathematical contributions to the whole thing, there's basically the cosmological constant which is attached to the gravitational field equations, which make for that it can be a fall of gravity, and that's a vanishing constant in the running constants. And this is well established by modern sky surveying experiment that the universe is flat. And these days a lot's going on with the sky survey. And then there's the mass energy equivalency, or E equals mc squared, and the idea that when something goes to approach the speed of light, that its mass goes to infinity because it can never go past the speed of light. And while that's somewhat a disconnect from the absolute relative motion of things in the linear, in their orbits or the passage of each other, there's in the rotational, it kind of seems to add up and build up and affect the regime of what results these effects in special and general relativity. Length contraction and time dilation, which I see as combined always, that it makes space contraction. And then the actual motion through the passage of space is as a body through space, in this line drawing context and all this sort of thing. So anyways, I found this book the other day that Einstein wrote, and in it, Out of My Later Years by Albert Einstein, published by the Philosophical Library of New York, he took some time from his professorship as a visiting fellow at the Institute for Advanced Study in Princeton, New Jersey, at Princeton, of his considerations of his realm and his opinion and his researches and his outlook in the study of physics. Now, after relativity came up and became established, and it became established largely for a couple of things. One was determining Mercury's precession around the sun. And when that added up, he got a lot of credit. And then another was in terms of light bending and following the geodesy, that although light is massless, that the image transmitted by light, it follows what we would call the space-time curvature, or at exactly the same passage as a massy object would follow, as if here it's massless, or kind of in these super classical models we've been talking about before, is that it's fallen in from all sides, and so that's just this natural rut or track. And then there's also some ideas that one might consider as like, wow, if you think of large bodies and the optical and lensing, about the wavelength of the very small wavelengths and high frequencies, that for large enough bodies that there's naturally focus as around them, and called Fresnel imaging. Whereas the Fresnel lens is most familiar as a very it's as a mirror, and it has a bunch of different pieces that kind of all focus the light beam to make what's called the lighthouse of a coast that is used to warn ships in the fog and at night away from destruction on the rocks or the reefs. The Fresnel lens is like a thing, but the Fresnel lensing and this kind of thing is also the ideas about how otherwise this wave-like property of light makes it so that it's like so. Then another thing that came after relativity was kind of accredited and shown and demonstrated and accepted as a theory, and because it reduces to the classical theory, of course, the Newtonian theory and its limit, and so on. Then there was quantum mechanics became around, the notion of the particle wave duality, kind of like as was just mentioned, the small wave large wave duality of optics and physics, and what could affect lensing is what's called gravitational lensing, Einstein cross, and this kind of thing. That there's as well then quantum mechanics. So quantum mechanics came up and about, and is after the discovery of the proton, neutron, and electron, subatomic particles, and establishing the monoelectron orbitals is what result for bonds. But long before, there was established the theory of polar solvents like water and their effect and behavior on bonds. And a long time before, there was stuff like van der Waals and ionic bonds. The covalent bonds were very well established, and they represent the material solids and the inorganic very well. But not necessarily so as with regards to, Zhabotinsky or reactions that oscillate and this kind of thing. But it became very clear that both relativity and quantum mechanics were very strong theories, and that as precise as experiments can be made, that it could be so contrived that according to trying to factor out other factors of the experiment, that for Michelson, Morley, and Pound-Rebka, and these kinds of things about the behavior of light and the transfer passage of ether in the terrestrial frame, that for quantum mechanics then, there was some things that were at play with regards to instantaneous things, or things that are infinite, instantaneous in two places at once and affected by a cause in one place, an effect in the other place with no elapsed time. And the notion there's no privileged frame that could so make that so. These are not necessarily competing things, but things contrasting things is what must be resolved. And so the quantum mechanics then has that the opinion either way, the theories of relativity and quantum mechanics is kind of like so. 100 years later, relativity has been proven out to 20 to 30 orders of magnitude. Though we'll kind of let it be about things in modern cosmological and sky survey that the inflationary epoch is found to kind of be contrived. Quantum mechanics as well, which is particles are stochastic and they behave kind of like waves if you keep adding them up by a law of large numbers, or it's continuum mechanics really. But also again proved out to 20 or 30 orders of decimal magnitude, which is as much smaller as the atom is than a person. 25 orders of magnitude by mass, or accordingly by length or distance. When that small, mass and length kind of interchange a little bit. So anyways, they're both shown in these contrived, lined up experiments to show that they're validated, and it's such precise, high energy experiments. But they disagree. So fundamentally, they're pointing the opposite way, and so it kind of begs this notion: well, where can we finally put a theory of gravity? What, gravity, the most fundamental force that anybody has ever heard of, physics-wise, is not included? Well, it goes in the middle, and the idea is that, or my idea is that instead of Newtonian pull gravity, it's because how can a perpetuum mobile or perpetual motion device be affected by all these things at once? They would run out of energy. It violates conservation of energy, the entire concept. Which is why it's not included in the theories, because they're based upon invariant theories and conservation laws. Or as I put it, with quasi-invariant theories and continuity laws. So anyways, the science is kind of at an odds, and it's kind of reflects on this, is that about 120 years ago, there was Kelvin, there was Rutherford, there was Rayleigh. And so Rayleigh kind of established something. It's like, hey, if we add up the energy from these light waves, this was before things were discretized, that energy bands of electron orbitals moved in discrete amounts, and that hydrogen lines and spectral lines were a given value, not a range. And that atoms were points and particles, and for the Pauli principle, that two atoms in an identical solid of the same kind are basically indistinguishable but always distinct. This ultraviolet catastrophe. And that was solved by getting things into finite terms, and there's the methods of analysis, the measurements of collection, and the measurements of detection for observation, sampling, and measurement effects came up. That's why what is our continuum mechanics all classically, which is geometries and forms and proportions and becomes discrete as about energy levels at the very small, And then we have a fixed constant for Planck, the Planck's constant, which relates to a fixed large constant for Avogadro, the molality of things, or molarity of things, in stoichiometric and moles for molecular chemistry, for atomic chemistry. Then it becomes that these are kinds of frames, as about that otherwise what's lacking is the analytical methods and the centrality of elements that have properties that make for a continuum mechanics that also happens to explain how these things are so, and leaves out for these backgrounds and having to sample and observe and measure off them how it results that those are the discrete values and those are the particles and those are the kinds of things that make for the ultraviolet catastrophe, is like the ultraviolet ultima ultraviolet, or, and here I'm kind of grasping for words in a sense, but the idea is that it's ultraviolet conquest or something, ultraviolet return, because these two competing theories cannot fundamentally agree unless they'll be able to pull back together, and that pretty much starts with having gravity in the middle not being a perpetual motion device and violating the laws of invariance and conservation. And as well that the constants reflect their ratios and forms and their activities, their actions, in these other usual principles, like principle of conservation, principle of least action, and otherwise principles of uniformity and centrality and ... That the theory needs for mathematics of why this can be, as it was built from the mathematics that it had, according to the techniques it had, according to the values it could sample, that after spectroscopy and its tremendous success, and something like in the standard candles of astronomy, its tremendous success and establishment of bases for measure and ultra precise measures in these 20 into 25 to 29 orders of decimal magnitude. These things, these most perfect things, that so results that it's even farther than that to get back together this continuum mechanics again. So I was very pleased to find this book on the shelf the other day, and so I procured it, and I've been reading a bit about it. And what is in it are some essays of his. These are mostly essays, I imagine, written in his later years. The title of his book is Out of My Later Years. They're his collected statements of a sort. And one thing I really enjoy about Einstein is that he is at once a lighthearted fellow and a somber fellow. And that he is at once a very careful hedge and a grandiose sort of totalitarian. And meaning that on the one hand, he'll be very careful how he frames things to not later allow himself to be proven wrong. And on the other hand, he'll frame things that will later be seen to include everything. He's a grandiose hedge, and I really appreciate that. And so some of his stories are about, his relationships with Zionism, and his relationships with his affairs and this and that. And then some of his stories are about his relationship with his religion and God, and that he affected a reflection many times upon his declared adherence to religion and monotheism, and that was part of the thing. That then what was that he's a grandiose hedge, and that it can be a compliment compared to somebody who's just a hedge and you can't expect anything from him, or someone who's just grandiose and they expect too much. That as a grandiose hedge, there's that his ideas of how to put together this idea that there's no absolute frame is reflected in what's called his total field theory. That the field, the space-time field, which is his geodesy and also particle physics and what all fits together, has to be a total field again. And so those kind of are what I'm searching for in his readings, and I'm going to read some pieces that he put down that really help encapsulate the definitions of relativity and really help encapsulate the definitions of special relativity and general relativity, and allow one to see why that really general relativity should be first and special relativity is last, although he released special relativity first and general relativity second, and most times people kind of put that cart before that horse. It's the other way around. Or in various senses, why today they say SR is local. SR is local, special relativity, whereas GR is a geodesy. So it's the instantaneously evaluated everywhere geodesy of all the world lines, and the rule is there are no closed time-like curves. Nothing ever goes backward in time. But it may go slower or meet any two given clocks. All right. So anyways, then if you take a look at this, what might read from it is where I'm at is, mechanics and the attempts to base all physics upon it. So I'm already at page 65 here, kind of. So I'll just kind of dog mark that. But what I wanted to do was to... Here, let me read the leaf. The publishers of this volume feel privileged in presenting this new collection of essays by the distinguished physicist whose deep human feelings and wisdom have endeared him not less to the average man than to the scientist and scholar. The book indicates that Albert Einstein's life and work are not confined to the problems of science alone. He is endowed with awareness of the most urgent questions of modern society: social, religious, educational, and racial relationships. Always an independent and uncompromising thinker, Dr. Einstein attempts to clarify in his papers the position of man unencumbered by traditional prejudices, inhibitions, and limitations in the world of today. This book will show Einstein the philosopher, Einstein the scientist, Einstein the man. It is a treasure of moving thought and a striking record of the titanic achievements of one of our most eminent contemporaries. Various parts of the volume deal with personal credos, politics, education, the Jewish issue, war and peace, and also the fundamental principles of physics. Here, that's really all that's of interest here, but the others can be appreciated as part of his hedge as being too impersonal. In several chapters, the author explains his theory of relativity in such simple terms as to be understood by every intelligent person. None of the essays were written before 1936, and many of them have never been published in any form. Okay. Here's a portrait of Einstein by Lori Jacobi. Albert Einstein. Einstein was well known to have wild hair, and he has a mustache, most usually, sometimes a brief beard, but mostly just the mustache. And I'm leafing back from the end, where much of the end of this work, the later pieces are devoted to Zionism, and I believe in Zionism and that Canaan is the land of the Canaanites, and both. What I wanted to read were just some of his pieces about. He gives some warnings about moral decay. He says that freedom is paramount. First of those two goals requires morals and emotions. Though our conduct seems so very different from that of the higher animals, the primary instincts are much alike in them and in us. One of his quotes is that animals are motivated by pleasure and fear. Then came the growth of the natural sciences with their great influence on thought and practical life, weakening still more in modern times the religious sentiment of the peoples. The causal and objective mode of thinking, though not necessarily in contradiction with the religious sphere, leaves in most people little room for a deepening religious sense. Early had written, the universal moral idea thus owed its original psychological potency to that link with religion. So here he's expressing that he relates morality and religion insofar as that you might imagine that at the time there was a very strong upswelling of what was called atheism, and the idea that which is not an irrational idea, it's empirically mostly so, but according to access to philosophy, that it's not scientific in a sense, so much as that it's comes along with science, matters as such. And that he continues with more pieces about science and religion, and he's a scientist, and he's in apologetics for people who have been disappointed by teachings that later disappoint them, their correlation with truth, or that it can reflect yet again this rejection of the humanism. Sometimes humanism is not humanism that the atheist point of view might have. I don't really believe in them. The theory of relativity. Chapter 10. Mathematics deals exclusively with the relations of concepts to each other without consideration of the relation to experience. Now here I'll interject comment. That's where this strong mathematical Platonism and the mathematical universe hypothesis has the same universe. But here he is expressing a Platonic notion that this is mathematics and it's its own thing. Physics, too, deals with mathematical concepts. However, these concepts attain physical content only by the clear determination of their relation to the objects of experience. He's expressing that physical experiments must be reproducible and have observables. This in particular is the case for the concepts of motion, space, and time. Motion, space, time. The theory of relativity is that physical theory which is based on a consistent physical interpretation of these three concepts. So he's already hedged himself as like, it's never wrong. The name theory of relativity is connected with the fact that motion from the point of view of possible experience always appears as the relative motion of one object with respect to another, e.g. of a car with respect to the ground, or the earth with respect to the sun and the fixed stars. It used to be that basically the stars' orientations with respect to each other never changed over all their observed time. But then there was found that besides the planets that were discovered because they track across the sky, the wanderers or planets, there's also been some findings later that there are stars that do appear to move, and otherwise these immobile celestial spheres. That the original theory pre-Copernican was kind of like the Earth is the center and it's surrounded by these 7 concentric spheres, each one immobile. And like on the inner ones are the planets, and on the outer ones are the stars. Explaining the images they saw layered together as a theory. And about the relative motion is to keep in mind that when you pass someone on the highway, you're each doing 60 miles an hour in opposite directions. And the last thing you each see each other then disappears because you passed each other. But that last image persists and it's gone. All right. Motion is never observable as motion with respect to space, or as it has been expressed as absolute motion. In relativity. The principle of relativity in its widest sense is contained in the statement, the totality of physical phenomena is of such a character that it gives no basis for the introduction of the concept of absolute motion, or shorter but less precise, there is no absolute motion. It might seem that our insight would gain little from such a negative statement. In reality, however, it is a strong restriction for the conceivable laws of nature. In this sense, there exists an analogy between the theory of relativity and thermodynamics. The latter two is based on a negative statement, there exists no perpetuum mobile. He has that as for thermodynamics, but it's about the conservation laws and symmetries in invariant theory. The development of the theory of relativity proceeded in 2 steps, special theory of relativity and general theory of relativity. The latter presumes the validity of the former as a limited case and is its consistent continuation. Here, this is where these days we say it's the other way around. General relativity first, special relativity, special case second. That is not shared by all people. For example, most people who observe the word Einstein as authoritative which I do too, given that it's derived the other way around, is the fair way to do things. A. Special theory of relativity. Physical interpretation of space and time in classical mechanics. Geometry, from a physical standpoint, is the totality of laws, according to which rigid bodies mutually at rest can be placed with respect to each other, e.g. a triangle consists of 3 rods whose ends touch permanently. It is assumed that with such an interpretation, Euclidean laws are valid. Here we've been having quite a discussion about Euclid, and Euclid's geometry is arising from a geometry of points and spaces. Space in this interpretation is in principle an infinite rigid body or skeleton to which the position of all other bodies is related, body of reference. So here you just said there's no absolute motion. Analytic geometry, Descartes, uses as the body of reference, which represents space, 3 mutually perpendicular rigid rods on which the coordinates xyz of space points are measured in the known manner as perpendicular projections with the aid of a rigid unit measure. This is kind of reflecting that Cartesian space with coordinates is Euclidean space equipped with the origin, and then that though it's orthogonal, the orthogonal vector space vector basis, E1, E2, E3, or E the unit orthonormal vector basis, it doesn't say what happens at the ends. And that's variously called non-Euclidean geometry, Lobachevskian geometry, Riemannian geometry, hyperbolic geometry, Kahn's-Knight commutative geometries, torsions, Sitter space, anti-de Sitter space. Anyways, this is Euclidean and it's Cartesian. Physics deals with events in space and time. To each event belongs, besides its place coordinates xyz, a time value t. The latter was considered measurable by a clock, ideal periodic process of negligible spatial extent. This clock c is to be considered at rest at one point in the coordinate system, e.g. at the coordinate origin x equals y equals 0. The time of an event taking place at a point p, xyz, is then defined as the time shown on the clock c simultaneously with the event. The event is the observable. The event is the value. It's a structural value. The event is the content of the space-time. Here the concept simultaneous was assumed as physically meaningful without special definition. This is a lack of exactness which seems harmless only since with the help of light, whose velocity is practically infinite from the point of view of daily experience, the simultaneity of spatially distanced events can apparently be decided immediately. The special theory of relativity removes this lack of precision by defining a simultaneity physically with the use of light signals. Time t of the event in p is the reading of the clock c at the time of arrival of a light signal emitting from the event, corrected with respect to the time needed for the light signal to travel the distance. This correction postulates that the velocity of light is constant. This allows one to use from an observer's perspective their own measurements to adjust distant measurements, and with respect to those, their passages is via the images that arrive from said object. This definition reduces the concept of simultaneity of spatially distant events to that of the simultaneity of events happening at the same place. Coincidence, namely the arrival of the light signal at C and the reading of C. Classical mechanics is based on Galileo's principle. A body is in rectilinear and uniform motion as long as other bodies do not act on it. There's a big difference between linear motion and rotational motion. That all bodies are always not at rest and they're in some linear or rotational motion with respect to every other body. Some people that have that, it works out that the atom is really a tiny, tiny, tiny gravitational singularity, a black hole. Some people have it that a related concept called the white hole is basically present everywhere with respect to gravity and this kind of thing, and that the Dirac positronic sea is kind of the same sort of space, that the virtual charged and massy, constantly annihilating and disappearing vacuum field is as such a milieu for differences. These, though, are later concepts which are generally introduced with respect to backgrounds from singular sorts of events, that otherwise these invariant theories about the continuity laws and symmetries run out to extremes at singular events. Galilean ... A body is in rectilinear and uniform motion as long as other bodies do not act on it. This statement cannot be valid for arbitrary moving systems of coordinates. So here he's saying that the origin is everywhere. There is an origin everywhere. And so in the course of each of these origins, until they converge and there's basically a collision or a meeting, that otherwise there's passage in orbits. So this helps reflect that orbits or an orbit is a pretty general way to say these things. And the fact that it works for all sorts of things, orbits, orbitals. We're orbiting the Earth, that we're at rest with it as we fall together in gravity's field, that the Earth is not working to pull us down. It just blocks the rest of the universe on the other sides. Slight falling push. And keeps us on the ground with the ability to establish an upright perspective. So, this statement cannot be valid for arbitrary moving systems of coordinates. It can claim validity only for so-called inertial systems, the Galileo's principle. So, an inertial systems is the contents of the frame. What is a frame? Well, it's an origin. It's a coordinate reference. Well, what's in a frame? More frames. What's outside a frame? It's in frames. Inertial systems are in rectilinear and uniform motion with respect to each other. For example, 0. In classical physics, laws claim validity only with respect to all inertial systems. Special principle of relativity. It is now easy to understand the dilemma which has led to the special theory of relativity. Experience and theory have gradually led to the conviction that light in empty space always travels with the same velocity c, independent of its color and the state of motion of the source of light. It's emitted, and the continuous time emission of light from its source travels with the source. It's also Doppler. The adjusting of frequency as is changed by the velocity of relative motion. Again, remember, all Einstein's relativity results in the classical when things are simple. The principle of the constancy of the velocity of light in the following referred to as L principle. L principle is that light's principle is that it's constant. And if we reflect on principles for a moment, then a lot farther along in the work, there's the Machian. And so Mach is Ernst Mach, and it's named for him Mach numbers, which is where Mach 1 is a measure of the speed of sound, or approximately 770 miles per hour. And the speed of sound in air is called Mach 1, that when you break the speed of sound, it is well known to be accompanied with what's called a sonic boom, and otherwise very strong effects that so result from the shock. And what happens in the acoustic. But Mach is known in physics for his field theories about the field. Is like, well, what if there's absolute or there's not absolute? So when we say the Machian principle, it really is in effect kind of like, what's the global and total? How is the global not the same as the total? But it's not as so much as for the local. So the L principle is light's principle here, and it's local. It's principle. Now, elementary intuitive considerations seem to show that the same light ray cannot move with respect to all inertial systems with the same velocity c. The L principle seems to contradict the special principle of relativity, which is in classical physics laws claim validity only with respect to all inertial systems. at a time. It turns out, however, that this contradiction is only an apparent one which is based essentially on the prejudice about the absolute character of time, or rather the simultaneity of distant events. We just saw the x, y, z, and t of an event can, for the moment, be defined only with respect to a certain chosen system of coordinates, the inertial system. There is no privileged frame is another way that relativity is sometimes stated. But when we're dealing with things on the Earth, it's called the terrestrial frame. And when we're dealing with things in the lab, it's called the laboratory frame. The transformation of the XYZ-T of events, which has to be carried out with the passage from one inertial system to another, coordinate transformation, is a problem which cannot be solved without special physical assumptions. However, the following postulate is exactly sufficient for a solution. The L principle holds for all inertial systems. Application of the special principle of relativity to the L principle. It depends. It's relative. What is received according to the passage of the speed of light? What can be measured by a clock? When, for example, the motion in the inertial system affects the speed of the clock because time is relative, but always forward. It's like Zeno's paradox with the Achilles and the tortoise. They're still both always going forward. Eventually they meet. Here, though, he is leaving out the fact is like, so we're not making an assumption about the light with respect to that. Light speed is still constant with respect to it, which it is. Locally, it's always just whatever the image happens to be. There's persistence of vision. The transformations thus defined, which are linear in x, y, z, t, are called Lorentz, L-O-R-E-N-T-Z, Lorentz transformations. Lorentz transformations are formally characterized by the demand that the expression dx squared plus dy squared plus dz squared minus c squared dt squared, which is formed from the coordinate differences dx, dy, dz, dt of two infinitely close events. Infinitesimally close, infinitely close. Be invariant, i.e. that though the transformation it goes over into the same expression formed, i.e. that through the transformation it goes over into the same expression formed from the coordinate differences in the new system. Here he's reflecting the observation that these things always move along in this way. And it carries on, it carries along. With the help of the Lorentz transformations, a special principle of relativity can be expressed thus. The laws of nature are invariant with respect to Lorentz transformations, i.e. a law of nature does not change its form if one introduces into it a new inertial system with the help of a Lorentz transformation on XYZT. Here, his law of nature is kind of a mathematical model that would have an interpretation as a physical model, a physical interpretation as a physical model. A law of nature is something along the lines of that there's no perpetuum mobile or something like that. Violation of the principle of least action, basically. But here it's to be said that when the laws of nature are reflected by invariant theory, that it also must be left out some room for singularity theory, which is in extremis what happens when those go around the corner. The special theory of relativity has led to a clear understanding of the physical concepts of space and time, and in connection with this, to a recognition of the behavior of moving measuring rods and clocks. It has in principle removed the concept of absolute simultaneity, and thereby also that of instantaneous action at a distance in the sense of Newton. It is made of freedom as about that. For example, for this space contraction, which usually developed in a couple separate lessons as length contraction and time dilation, which put together make this space contraction, and the retardation of clocks until such time as they join and immediately meet and pass at the same time together. This is where basically when Achilles catches up with the tortoise, for the second the tortoise sees Achilles and Achilles sees the tortoise. It's peripheral. Peripheral parallax is one way to talk about this. Parallax is the application of triangulation or angles to kind of determine via stereoscopic imaging when the location of things, which is the usual way that people see things and that. And then the peripheral is as of about the peripheral vision. Peripheral parallax is this concept as of about the sides. Peripheral parallax. A law of nature, with the help of Lorentz transformation on XYZT. He's basically saying that this is the invariance. And here, that our Lorentz transformations is not like the Galilean. It has built-in light speed as a constant. And that's imaging, and it's so observable, and so it's reflected in anything that's an observable, which is not necessarily much visual, but lives in the same realm and milieu as light speed in a vacuum. Where light is optical light, that when we talk about electromagnetic radiation is radio frequency emissions, and the infrared as thermal emissions, that they both still establish their presence in the same realm. There's that optical light really is kind of special. And then with regards to electrical current in a conductor, it's very, very fast, and it's like only a couple orders of magnitude less than light speed in a vacuum. And it kind of behaves as if that were a constant that it goes to. That it's radionic, slower than light. But light speed in a vacuum is yet tachyonic to any other medium that light goes through. It's faster than light through a medium, right? And it has a certain fixed speed, c, the speed of light, about 10 to the 8th meters per second times 2.98 ... A particular quantity that is not just exactly 3.00 times 10 to the 8th meters per second. With regards to the parsec. The special theory of relativity has led to a clear understanding of the physical concepts of space and time, and in connection with this, to a recognition of the behavior of moving measuring rods and clocks. It has in principle removed the concept of absolute simultaneity, and thereby also that of instantaneous action at a distance in the sense of Newton. It is made for mass energy equivalency to arrive at space contraction in linear motion and gravitational singularity in rotational motion. It has shown how the laws of motion must be modified in dealing with motions that are not negligibly small as compared with the velocity of light. It has led to a formal clarification of Maxwell's equations of the electromagnetic field. In particular, has led to an understanding of the essential oneness of the electric and the magnetic field. And this is the theory of some potentials, that the real is this oneness. And besides that, according to Maxwell's relations, those are the electric and magnetic field show the electromotive force with respect to each other, and motion and passage and current in one, and motion and passage and current in the other. It has unified the laws of conservation of momentum and of energy into one single law, and has demonstrated the equivalence of mass and energy. Momentum is not a conserved quantity, is kind of like that this energy is pretty much a conserved quantity. And so that's matter or charge. And then this idea that this momentum is different is that this unification of these to one thing has that they're also separable. So it's basically conflated those two notions. And so momentum is about torque, and the static and dynamic is a thing that I wish I better understood, because there's lots of interesting things that can be made in mechanics and mechanical engineering that are in effect as of basically about momentum. And things like in statistics and probability, the moment generating function is another relevant thing to momentae. And what things happen that are changes in an instant, not just rates, but changes. From a formal point of view, one may characterize the achievement of the special theory of relativity thus. It has shown generally the role which the universal constant c, velocity of light, plays in the laws of nature, and has demonstrated that there exists a close connection between the form in which time on the one hand and the spatial coordinates on the other hand enter into the laws of nature. When this is the only theory that you have, that's the law. And given that it includes otherwise all of the Newtonian Galilean theory and Maxwell's theory, it works great. General theory of relativity, section B. I'm just going to read through this a little bit faster, I suppose, and save some of my comment for the end. Again, I kind of give my comment in this kind of tone and read Einstein's comment as in tone, which is forthright, upcoming, and sincere and sure. The special theory of relativity retained the basis of classical mechanics in one fundamental point, namely the statement, the laws of nature are valid only with respect to inertial systems. The permissible transformations for the coordinates, i.e. those which leave the form of laws unchanged, are exclusively the linear Lorentz transformations. Is this restriction really founded in physical facts? The following argument convincingly denies it. Principle of equivalence. A body has an inertial mass, resistance to acceleration, and a heavy mass, which determines the weight of the body in a given gravitational field, e.g. that of the surface of the Earth. These two quantities, so different according to their definition, are according to experience measured by one and the same number. There must be a deeper reason for this. The fact can also be described thus. In a gravitational field, different masses receive the same acceleration. Finally, it can also be expressed thus. Bodies in a gravitational field behave as in the absence of a gravitational field if, in the latter case, the system of reference used is a uniformly accelerated coordinate system instead of an inertial system. Here, the relationship between inertia and momenta is a big deal. And with regards to the uniformly accelerated as otherwise that acceleration has two parts. For this Newton's zeroth laws of motion, it is a matter for deconstructive fundaments. There seems, therefore, to be no reason to ban the following interpretation of the latter case. One considers the system of being at rest and considers the apparent gravitational field which exists with respect to it as a real one. This gravitational field generated by the acceleration of the coordinate system would, of course, be of an unlimited extent in such a way that it could not be caused by gravitational masses in a finite region. However, if we are looking for a field-like theory, this fact need not deter us. With this interpretation of the inertial system loses its meaning. One has an explanation for the equality of heavy and inertial mass. The same property of matter appears as weight or as inertia, depending on the mode of description. Here, basically, for quantum physics, it's mass because that reflects, according to Avogadro's number, the molarity of a mole, and that 1 mole plus 1 mole equals 1 mole of a perfectly consumed reaction. And then the weight is inertial, and it's in these systems of inertia and reflects what acceleration needs to occur to affect work. Considered formally, the emission of a coordinate system which is accelerated with respect to the original inertial coordinates means the emission of nonlinear coordinate transformations, hence a mighty enlargement of the idea of invariance, i.e. the principle of relativity. I like the idea that maybe he's saying, for example, singularities, because by now in his writing, Einstein is well aware of, for example, the concept of the black hole, a gravitational singularity, and otherwise has had a chance to watch the field mature for 30 years. First, a penetrating discussion using the results of the special theory of relativity shows that with such a generalization that coordinates can no longer be interpreted directly as the results of measurements. Only the coordinate difference, together with the field quantities which describe the gravitational field, determine measurable distances between events. After one has found oneself forced to admit nonlinear coordinate transformations as transformations between equivalent coordinate systems, The simplest demand appears to admit all continuous coordinate transformations which form a group, i.e. to admit arbitrary curvilinear coordinate systems in which the fields are described by regular functions. General principle of relativity. This is a hedge. And it's also grandiose. But it's not very much a call. Nor does it make so much predictive value. But it does allow these other concerns about the inertial systems to make their own. Now, it is not difficult to understand why the general principle of relativity, on the basis of the equivalence principle, has led to a theory of gravitation. There's a special kind of space whose physical structure field we can presume is precisely known on the basis of the special theory of relativity. See, this is a sort of hoisting oneself by their own bootstraps, or constraining for a frame these things, and resulting why the geodesy is a simple occurrence. Although again, why the light follows the track is a very particular thing. He goes on, this is empty space without electromagnetic field and without matter. It is completely determined by its metric property. Let dx naught, dy naught, dz naught, dt naught be the coordinate differences of two infinitesimally near points, events. Then 1. d squared plus dx naught squared plus dy naught squared plus dz naught squared, that quantity, minus this quantity, c squared dt naught squared. That's the ds squared, or the metric. And we've been discussing this in terms of the path integral, and about the Jordan measure and the line continuity and the quadrature and the field continuity and the Dirichlet function and the signal continuity and the mensuration of these things. It is a measurable quantity which is independent of the special choice of the inertial system. He's saying it is measurable in the sense that they add up to making something that's measurable after it's observable. That this analytical region is the nilvalent. It's not nil square or what. It's as of accords to, as we've been talking about, the infinitesimals and the raw differentials, that has analytical character. It's measurable. If one introduces into space the new coordinates x1, x2, x3, x4 through a general transformation of coordinates, then the quantity ds squared for the same pair of points has an expression in the form ds squared equals sum g ik dx dx to the I dx to the k, summed for I and k from 1 to 4, where g sub ik equals g sub ki, or perhaps that's lk, ik. So this is often what makes up for this covariant or coordinate-free coordinate tensor notation, but summation. But also it attaches this to that, because otherwise that's usual just as a matter of tensorial products, but also he's assigning its relevance to this measure. The GIK, which forms a symmetric tensor, and are continuous functions of x1 x4, then describe, according to this principle of equivalence, a gravitational field of a special kind, namely one which can be retransformed to the form 1, which builds that the metric exists in the Lorentz. At any given point in time, anywhere, so everywhere, but that goes without saying, because it's just a matter of this empty space without electromagnetic field and without matter. From Riemann's investigations on metric spaces, the mathematical properties of this GIK field can be given exactly, Riemann condition. However, what we are looking for are the equations satisfied by general gravitational fields. That basically reflects inverse square, and why orbits work different than just always pointing to the center or the locus of a massive body's object, but that it blocks all around And as you get out of the shadow of it, that it falls off. But while you're incident to it, that it's exact. This helps explain why galaxies are explained by Mond as to why there's no dark matter, which you'll notice is nowhere in this theory. That would be unscientific and unmathematical here. Just because that's its whole explanatory factor is like, this is the factor that's left over. How are we going to put this back into this model? From Riemann's investigations on metric spaces, the mathematical properties, it is natural to assume that they too can be described as tensor fields of the type GIK. So here, when he says it is natural to assume, that reminds us some of the language from Swanson's book. You know, it's easy, it's simple, it's clear, it's obvious, it's natural. To assume that they too can be described as tensor fields of the type GIK, these Riemann conditions of the spaces, these functions, the field, which in general do not admit a transformation to the form 1, i.e. which do not satisfy the Riemann condition but weaker conditions, these degenerate pseudo quasi conditions, which somehow add back up. Which, just as the Riemann conditions are independent of the choice of coordinates, i.e. are generally invariant. He's saying that, well, if it's not invariant, there must be some higher level invariance. And this is kind of explained in terms of continuity laws with respect to, well, what's the highest invariance? And it's like, well, hopefully it's something like fall of gravity's space-contraction, because that would leave things simple. A simple formal consideration leads to weaker conditions which are closely connected with Riemann condition. In fact, insofar as they diverge from it, it's as of matters of this quasi-invariance. They call it quasi-invariance in invariant theory. These conditions are the very equations of the pure gravitational field on the outside of matter and at the absence of an electromagnetic field. This is fair, and it's also descriptive in the terms that it's non-judgmental, and that a lot of people read wrongly, or they make wrong assumptions that they are building what they have this as a strong condition, when, as Einstein puts it, that it's a condition which is justified generously. These equations yield Newton's equations of gravitational mechanics as an approximate law, and in addition certain small effects which have been confirmed by observation. Deflection of light by the gravitational field of a star, influence of the gravitational potential on the frequency of emitted light, slow rotation of the elliptic circuits of planets, perihelion motion of the planet Mercury. They further yield an explanation for the expanding motion of galactic systems, which is manifested by the redshift of the light emitted from these systems. He had to have that. That's the idea of the gravitational constant, or cosmological constant, and since the universe was found flat along 25 years ago or 20 years ago, and 2 mass, this experiment, the number 2 MASS, a mass spectrometry type thing, but an observatory or sky survey, has that. That's the explanation that's left off with that Einstein's cosmological constant, which he called my greatest blunder, is still in these equations. Its value is indeterminate. He completes this chapter. The general theory of relativity is as yet incomplete insofar as it has been able to apply the general principle of relativity satisfactorily only to gravitational fields but not to the total field. We do not yet know with certainty by what mathematical mechanism the total field in space is to be described and what the general invariant laws are to which the total field is subject. One thing, however, seems certain, namely that the general principle of relativity will prove a necessary and effective tool for the solution of the problem of the total field. All right. Well, that's Einstein's definition of special and general relativity. And it's nice to kind of have an idea of how that fits in with all these discussions about the path integral and the continuum mechanics behind that, and the metric in space, and what happens when those things are let out, you know, and why these conditions are strong or weak, what there is of the the weaker, or the degenerate, the pseudo, the quasi, the underneath, the fundamental, the elements, which arrive at why these things are this theory of the sum potentials, or all the potentials. That it's nice to read something like that in such a short self-contained section. Then, as far as Einstein's opinion is concerned, he's just told us that that's it. Right. So then chapter 11 says E equals mc squared. E is the energy, m is the mass, c is the speed of light. If you were to convert mass to energy, the energy released would be as in terms of the mass times the speed of light squared. This is most famous is that the liberation by fission, nuclear fission of a nuclear explosion emits this much energy, or that also that in nuclear reactors it emits this much energy. Where we have gravity, which has this real graviton, the atom, that's a little white hole and black hole that sits in the Dirac positronic sea, and also this empty space of Einstein, full of things, has a strong nuclear force which holds it together, except all the subatomic particles are free in the middle, like they're falling together and orbiting. They're not a clump, they don't gravitate, they're not working, just kind of there. Then the charge is the electrons or their motion, where electrons are a big cloud, and they have many models that sort of reflect them accurately. Static and dynamic torque, electrical torque with regards to angular momentum. And here I'm just carrying forward a little bit about the equivalence, as he puts it, of mass and energy. That those are the first two forces, the electrical force after the strong nuclear force. Then there's the weak nuclear force, and the electroweak force. That those comprise basically what we call transmutation of elements, or the nuclear reactions. It's both of those in terms of emission and radiation and conversion of matter to energy, and matter in its transmutation according to elements and nuclear theory. And where iron is about the center of the nuclear elements. If there's one element in the center of all of atomic transmutation, it's iron. All right. I hope you enjoyed this reading today, and what it was about was Einstein's out of my later years, and that if you wondered what is the theory of relativity, and what are the theories of special relativity and general relativity according to Einstein, you need to look no further than Albert Einstein himself. And that everything else associated with it, in terms of anything else associated with it, with like space contraction as length contraction plus time dilation, or this total field, or the Machian, or rotational differences about mass energy equivalence, and linear motion with regards to images and sources and origins, and all this kind of stuff about the geodesy, and why light is like so, and why it was like so that his equations had to include the Big Bang's prediction of an expanding universe, and that's not so much so today. All that is on the side. And the next chapter, which I read already, it has it ends with a really great defense of Newton. And one thing about Einstein being such a great, grandiose hedge is that he gives a very strong defense of Newton. That no matter what else happens, Newton's still right. And it's the same for Einstein too. All right, great. Having a great day. So long.